We already discussed about thermodynamics and different process of thermodynamics, that is isothermal, isobaric, isochoric and adiabatic process. We also discussed the zeroth law of thermodynamics. Today let us discuss the topic first law of thermodynamics.
So let us discuss about the first law of thermodynamics. In first law of thermodynamics, we are dealing with the work done and change in internal energy and heat given to a system. Normally, we can explain the first law as, suppose we have a system and we give Q amount of heat to the system. So after taking the amount of heat, of course, when the heat is absorbed by the system, its temperature increases. So there is as a result of this absorption of heat, there is a tendency to increase its temperature. Of course, if also the system will do some work. So we know that the heat given to the system or the amount of energy given to a system is, if it is notated by the letter Q, and we know that the internal energy is normally measured as its temperature. Internal energy have a lot of parts. It have kinetic energy, potential energy, etc. Nuclear energy, atomic energy, all are included in the internal energy of the system. But normally internal energy is the measurement of kinetic energy. Of course, kinetic energy is a function of temperature. We normally measure the internal energy as the temperature of the system. So, if the system changes after taking Q amount of heat, the system changes from its internal energy state U1 to U2. The change in internal energy is U2 minus U1. So, normally we measure the change in internal energy. The change in internal energy is measured as the change in temperature. Okay. So, it's a function of course, internal energy is a function of temperature. So, in first law, suppose Q amount of heat is given to a system and the system used some amount of heat to increase its internal energy from U1 to U2. So, what is the change in internal energy? That is U2 minus U1. So, the heat is used to increase the internal energy, and also the system will do some work using that amount of heat absorbed. So it can be written as Q is equal to U2 minus U1 plus W. This is known as the first law of thermodynamics. Suppose delta Q amount of heat is absorbed. Delta Q is very small amount. Okay. So delta Q amount of heat is absorbed by the system. As a result of its absorption, suppose its internal energy is change is du, and also the system do some work, that is delta W. We can write delta Q is equal to du plus delta W. So normally we written first law in this form also, or we can write dq is equal to du plus p dv. We already studied that what is the work done by the system is nothing but p into dv. dv is a change in volume. So we can write dq is equal to du plus p dv. Okay. So the first law of thermodynamics is nothing but the law of conservation of energy. In law of conservation of energy, we already studied that the energy can neither be created nor be destroyed. Similarly, when we give some amount of energy to the system, it will utilize that energy, or it will utilize that heat to increase its energy, that is internal energy, and also use some amount of heat to do some mechanical work, dW. Suppose we have a piston like this. Suppose this is a piston and there is a working substance is here. If we give a dq amount of heat to the system, using that dq amount of the system will, there is an increase in the temperature of the system that will contribute to its change in internal energy. Also, the system will push this piston in the outward direction. So there is an expansion. So work is done by the system for expansion. So that can be written as dq is equal to du plus pdv. Okay. Normally, work done by the system is taken as positive. So, significance of first law of thermodynamics. So, it will give a concept of internal energy. It introduces the concept of internal energy, and also it is applicable to any process by which the system undergo a physical or chemical change. So, we can apply the first law to all processes. Okay. But there will be, of course there will be some change change in the equation due to in different processes like isothermal, isobaric, isochoric. അതായത് ഡിഫറെന്റ് പ്രോസസ്സുകളിലേക്ക് പോകുമ്പോൾ ഈ ഫസ്റ്റ് ലോ can apply to all the systems, whether it may be isothermal, whether it may be adiabatic. It is applicable to all type of systems. So the depends upon the conditions, there will be small changes in the first law. Okay, so we have to rewrite the first law according to that conditions. Second one, it will give you an idea about the internal energy. What is the change in internal energy? That is Q minus W. So it provides an equation for the change in internal energy. So also this method is used to determine the change in that are the applications of the or the significance of the first law. Okay, then what are the limitations of the first law of thermodynamics? So this law will not specify the condition under which the system can use its heat energy to produce some mechanical work. According to this first law of thermodynamics, it will not specify when the heat will absorb and when it will do some work, etc. It will not give any idea about that. And also it does not say how much heat energy can be converted into work. Whether the total heat absorbed can be converted into work or not. The first law will not say anything about the conversion of heat energy into work. Okay, that are the limitations of the first law of thermodynamics. എത്ര എമൗണ്ട് ഹീറ്റിനെ വർക്കാക്കി സിസ്റ്റത്തിന് മാറ്റാം എന്നതിനെ കുറിച്ചിട്ട് ഫസ്റ്റ് ലോ ഒന്നും പറയുന്നില്ല. അത് അതിന്റെ ഒരു ലിമിറ്റേഷൻ ആണ്. ഓക്കെ. So let us discuss about the specific heat of a gas. So what is specific heat of a material? Normally, suppose a substance of mass m have q amount of heat required to rise its temperature through delta T degrees. Okay, so what will be the heat required to increase the temperature of unit mass of a substance through 1 degree or through unit temperature? So, or through 1 degree. It is known as the specific heat of that material. Specific heat of that material. Suppose delta Q is the heat required to rise the temperature of a mass through delta T degree. അതായത് m mass ഉള്ള വസ്തുവിന്റെ ടെമ്പറേച്ചർ and 9 മണിക്കൊക്കെ പോകാൻ പറ്റുന്ന താല്പര്യം. അതായത് Q amount of heat is നമ്മുടെ ഒരു ബോഡി ഓഫ് മാസ് എം ഉള്ള ഒരു ബോഡിയുടെ ടെമ്പറേച്ചർ ഡെൽറ്റ ടി ഡിഗ്രി ഇൻക്രീസ് ചെയ്യാൻ ആവശ്യമുള്ള ഹീറ്റ് ആണ് Q എങ്കിൽ what will be the amount of heat required to rise the temperature of unit mass? Unit massന്റെ ടെമ്പറേച്ചർ ഇൻക്രീസിന് ആവശ്യമുള്ള ഹീറ്റ് എന്തായിരിക്കും? Q by m ആയിരിക്കും. And യൂണിറ്റ് ടെമ്പറേച്ചർ ഡെൽറ്റ ടി ടെമ്പറേച്ചർ ഇൻക്രീസ് ചെയ്യാനുള്ള യൂണിറ്റ് മാസ് ഉള്ള ബോഡിയുടെ ടെമ്പറേച്ചർ ഡെൽറ്റ ടി ഡിഗ്രി ഇൻക്രീസ് ചെയ്യാൻ ആവശ്യമുള്ള ടെമ്പറേച്ചർ ആണ് Q by m. അങ്ങനെയാണെങ്കിൽ ഒരു 1 ഡിഗ്രി അതായത് യൂണിറ്റ് മാസിന്റെ ടെമ്പറേച്ചർ 1 ഡിഗ്രി ഇൻക്രീസ് ചെയ്യാൻ ആവശ്യമുള്ള ഹീറ്റ് എത്രയാണ്? സോ ദാറ്റ് ഈസ് ഗിവൺ ബൈ Q ഡിവൈഡഡ് ബൈ m delta T. So this is known as the specific heat capacity of that material. So this is exactly same in the case of liquids and solids. But in the case of gases, we know that C is equal to Q divided by M delta T. But when we compress the gas without giving any heat, there is a tendency for increase its temperature. So this term becomes 0. So that is the that is a problem connected with finding out the specific heat capacity of gases. So normally we express the specific heat capacity of gases at specific conditions. Okay, that is known as CV and CP. So similarly, when we expand the gas freely, it increases without its temperature decreases without uh, any rise. It may expand without any rise in the temperature. So at that case, delta T is equal to 0. So Q divided by MC M0, that may be infinity. So due to these two reasons, we are normally specify heat of a gas at certain condition. That is, normally we calculate the specific heat of a gas at constant pressure and specific heat of a gas at constant volume. So in order to keep this heat pressure constant, and in order to keep the volume constant, it needs some amount of heat. Okay, so Cp and C. So what is Cp? Cp is specific heat at constant pressure. So this is defined as the amount of heat required to rise the temperature of unit mass of a gas through 1 Kelvin at constant pressure. So Cp is equal to delta Q by delta T or dot T. This is small amount, so we are using this delta Q by dot T at constant pressure, or this can be written as dot Q by dot T also, constant pressure. So the specific heat at constant volume is written as delta Q divided by dot T at constant volume. It is the amount of heat required to rise the temperature of unit mass of a gas through 1 Kelvin at constant volume. So this is known as CV and this is known as CP. Okay. So from the first law we know that dq is equal to du plus pdv. So let us analyze this equation at different conditions. What happened to this equation in the case of an if the temperature is constant, that is isothermal process. So in the case of an isothermal process, we know that the temperature is always a constant in the case of an isothermal process. So in order to keep the temperature of a system constant, okay, heat may absorbed by the system or heat may rejected by the system to make the temperature constant. One thing is clear, that in the case of an isothermal system, the temperature is always constant. So what is du? Du is measured as the change in temperature. If there is no change in temperature, du is equal to 0. So in the case of an isothermal process, du is equal to 0. At that case, the first law is equal to dq is equal to pdv. So this is the first law in the case of an isothermal process. In isothermal process, what happened? dq is equal to pdv. So let us discuss what about the adiabatic process. So in the case of an adiabatic process, we know that in adiabatic process, the walls are insulating one. There will not be any absorption or rejection of heat from the system to the surrounding. So the amount of heat entered or the leaving from the system is equal to 0. At that time, what will be dq? dq is equal to 0 in the case of an adiabatic process. So when we write the first law of equation for adiabatic process, we can write that du plus pdv is equal to 0. So what about iso choric process? In isochoric process, we know that the volume is constant. Volume means constant, means dv is equal to 0. So in the case of an isochoric process, dq is equal to du. And in the case of an isobaric process, there is no change. dq is equal to du plus pdv. Okay, these are the first law of thermodynamics at different conditions. When the system is in isothermal process, isobaric process, isochoric process, or is adiabatic process. So we discussed about the first law at different processes. Okay. So now we are discussing about the application of first law of thermodynamics. Here we are going to apply the first. What are the application of first law of thermodynamics? Here we are discussing the proof of Mayer's equation. You know that Mayer's equation is Cp minus Cv is equal to R is the Mayer's equation. Now we are going to derive the Mayer's equation from the first law of thermodynamics. That is the one of the application of first law of thermodynamics. So you should be careful while doing these operations. Okay. So first of this, let us take the internal energy as a function of V and T. Okay, of course internal energy is a function of P, V and T. We already fixed two terms V and T, so there is no need of fixing pressure because PV is equal to nRT. So from this equation, suppose we are taking internal energy as a function of V and T. So what will be the small change in the internal energy du? That may be due to change in volume or it may be due to change in temperature. So it can be written as du is equal to dou u by dou v at constant temperature into dV. And also plus this is the change in the internal energy due to temperature. So that can be written as dou u by dou t. Here we are taking volume as a constant into dt. So du can be written as dou u by dou v at constant temperature into dV plus dou u by dou t at constant volume into t. Here we are calculating the change in u, okay, internal energy due to change in volume and change in temperature. Okay, so this can be written as this. So we already know from the first law of thermodynamics is that dq is equal to du plus p dw, or we can write dq is equal to du, dw can be written as p dv. So next we are going to substitute du from this equation. Okay, so we can write dq is equal to du plus p dv. That can be written as dq is equal to dou u by dou v into dv plus dou u by dou t into dt plus p dv. And we are dividing this through dt. So we can write dq by dt is equal to dou u by dou v is here into dv by dt. So we are dividing with dt. So here dt dou u by dou t at constant volume into dt divided by dt. So that term cancels. So here there is only one term, that is dou u by dou t at constant volume, plus here we have p dv. When we divide this with dt, you will get p into dv by dt. So that is the equation. So we are taking dv by dt is here in this equation, also here. So we are taking it common outside. So dq by dt is equal to dou u by dou t at constant volume. So this is dou u by dou t at constant volume plus p, we are taking dv by dt outside. So p plus dou u by dou v at constant temperature into dv by dt. It is constant to these two terms. So we can take dv by dt outside. So now we are applying the condition. If the gas is heated and under constant volume, that is dv by dt at constant volume means, so we have to take constant volume condition. We have to apply the constant volume condition for this equation. So this term will be dq by dt at constant volume. It's already, the term is du by dt at constant volume. It is already there. Okay, in all this equation it is there that dou u by dou t is always under constant volume. plus P into dou U by dou V into dV by dt. So what will be dV by dt at constant volume? Constant volume means dV is equal to 0. So this term will be vanish. So you will get the expression as dQ by dt at constant volume is equal to this term. That is dou U by dou T at constant volume. So what is dQ by dt at constant volume? It is nothing but Cv. We already discussed that Cv is the heat, the Cv is equal to dQ by dt at constant volume. So this is dQ by dt at constant volume is equal to Cv. In this particular case, dQ by dt at constant volume is equal to dou U by dou T at constant volume, that is equal to Cv. So suppose the gas is heated at constant pressure. So we have to apply the constant pressure condition to this equation. Okay, so you will get dou Q by dou T at constant pressure. This term is always in constant volume. We can replace this term by Cv. So dQ by dt at constant pressure is equal to Cv. This term is replaced by Cv plus this equation is P plus dou U by dou V into dV by dt at constant pressure. So here we are applying the condition in this case dQ by dt at constant, when dQ by dt is at constant pressure, this is in constant pressure. So when we apply or when we heat the system under constant pressure, this equation is converted into this type equation. So in the case of an ideal gas, we know that at this term, this is already dou U by dou T at constant volume, and here also dou U by dou T at constant volume. Here also dou U by dou T at constant volume. What will be change in internal energy at constant volume? This term is already 0 because at constant temperature there will not be any change in internal energy. So in the case of an ideal gas, dou U by dou V at constant temperature is equal to 0. So we can rewrite this equation as this. What is dQ by dt at constant pressure? It is nothing but Cp. So we replace dQ by dt at constant pressure as Cp plus Cv plus P into this term vanishes, P into dV by dt at constant pressure. So next we are going to calculate what is dV by dt at constant pressure. So in order to calculate dV by dt at constant pressure, we have to write the ideal gas equation, that is PV is equal to RT. So when we differentiate this equation, partial differential, that is P ഒരു term constant ആക്കി മറ്റേതിനെ differentiate ചെയ്യുക, next അതിനെ constant ആക്കി അടുത്ത term differentiate ചെയ്യുക. So here P taken as a constant. So P dV at constant pressure, all these things are happen at constant pressure. So P dV at constant pressure plus V dP. When we differentiate, first we differentiate dV by taking P as a constant. So P dV at constant pressure plus we taking V as a constant, differentiating P. So V dP at constant pressure is equal to R into dt. So at constant pressure, what is dP? Change in pressure at constant pressure is 0. So this term will vanish. So you will get P dV at constant pressure is equal to R into dt. So this equation is P into dV by dt. When we divide this, when we taking dt into this side, we can write the equation P into dV by dt is equal to R. So we can replace P into dV by dt at constant pressure by R. So this equation will become Cp is equal to Cv plus R, or Cp minus Cv is equal to R. So hence we proved the Mayer's equation from first law of thermodynamics. നമ്മൾ already adiabatic process in the equation of state discuss ചെയ്തു. എന്തായിരുന്നു adiabatic process in the equation of state? That is P varies to gamma is a constant. Now we will derive, or we can derive the equation of state for an adiabatic process, that is P varies to gamma is a constant from first law of thermodynamics. So that is the adiabatic equation. So now we are going to find out the adiabatic equation from the first law of thermodynamics. So we know that from the first law of thermodynamics, delta Q is equal to du plus pdv. We already we already discussed that for adiabatic process there is no heat absorption or rejection, so delta Q is equal to 0. So we can rewrite this equation as 0 is equal to du plus pdv, or we can write du is equal to so we know that what is CV? CV is dou Q by dou T at constant volume. So when we find out dou Q by dou T at constant volume from this equation, we know that dou Q by dou T is equal to dou U by dou T. Dou Q by dou T. CV is a specific heat capacity at constant volume. So when we can calculate the specific heat capacity at constant volume from the first law of thermodynamics. So now here delta Q is equal to du plus pdv. At constant volume, what happened to pdv? That term vanishes. So when we take delta Q by delta T at constant volume, you will get this as dou U by dou V at constant volume. So what is delta Q by delta T at constant volume? That is nothing but CV at constant volume. So CV is equal to, or CV is itself constant for constant volume, specific heat capacity at constant volume. So this delta Q by delta T or CV can be written as du by dt at constant volume. So from or we can write du is equal to CV into dt. CV is nothing but du by dt at constant volume, or that is equal to CV. So du can be written as CV into dt. So we can rewrite this dq as 0 is equal to CV dt plus pdv. Okay, for 1 mole of a gas, the ideal gas equation can be written as PV is equal to RT. Okay, so when we differentiate this equation, what happened? PdV plus VdP is equal to RdT. So substituting this in equation 24, we can write this is equal to, we are going to write dt as PdV plus VdP divided by R. So here in this equation, we are going to substitute for dt. So that is equal to 0 is equal to CV into what is dt? From this equation, dt is nothing but pdv plus vdp divided by r. So this is equal to CV into pdv plus vdp divided by r plus this term is the pdv. So this can be written as CV into pdv plus vdp into r pdv. So r is came from this expression. So when we take r outside, we have to multiply this with r. Then only we can take r into that side, left hand side of the equation. So when we take an r from here, we have to multiply prdv divided by r. So the equation will like here. So what is r? R is nothing but Cp minus Cv. So നമ്മുടെ ഇക്വേഷനിൽ ആറിന് പകരം Cp minus Cv എന്ന് കൊടുത്താൽ നമ്മുടെ ഇക്വേഷൻ ഇങ്ങനെയായി. Cv pdv ഇവിടെ ഉണ്ട്, and Cv vdp is also here. So we are going to give an r as Cp minus Cv. So this is Cp minus Cv into pdv. So this is the equation. So this is our equation, that is 0 is equal to Cv pdv plus Cv vdp plus Cp minus Cv into pdv. So when we distribute this, or when we apply distribution law to this case, you will get Cv pdv here, Cv vdp. So this is Cp pdv minus Cv pdv. Here Cv pdv get cancelled. So you will get Cv vdp plus Cp pdv. So when we divide through Cv, what you will get? 0 is equal to dp divided by, we divide through pv dv. Okay, pv dv കൊണ്ട് ഈ ഇക്വേഷനെ ഡിവൈഡ് ചെയ്യുമ്പോൾ ഇവിടെ വി ഡി പി പോയിട്ട് ഒരു പി താഴെ, ഡിനോമിനേറ്റർ ഒരു പി വരും. പി വി ഡി പി അല്ലേ, അപ്പൊ വി ഡി പി ഓൾറെഡി ഇവിടെ ഉണ്ട്, അത് ക്യാൻസൽ ആയി പോകും. ഇവിടെ നിന്ന് പി വി ഡി പി കൊണ്ട് ഡിവൈഡ് ചെയ്യുമ്പോൾ പി ക്യാൻസൽ ആയി പോകും. അപ്പോൾ അവിടെ എന്തുണ്ടാവും CP/CV അവിടെ ഉണ്ടാവും, അതേപോലെ dV/V. സോ ദിസ് വിൽ ബിക്കം dP/P plus CP/CV into dV/V. So what is CP/CV? We already know that CP/CV is nothing but gamma. Okay. This gamma is known as the ratio of specificity. So this can be written as dP/P into gamma dV is equal to 0. Equation എങ്ങനെയായി മാറി? dP/P plus CP/CV is gamma into dV/V. So when we integrate this equation, you will get, when integrate ചെയ്യുമ്പോൾ, what is dP/P? When we integrate dP/P, you will get ln of P, natural logarithm of P. Gamma അവിടെ ഉണ്ട്, ഇത് എന്ന് പറയുന്നത് natural logarithm of volume. So that is a constant. So we know that ln P plus ln V, gamma ln V എന്ന് പറയുമ്പോൾ എന്താവും? ഗാമ എന്ന് പറയുന്ന ഇവിടുന്ന് മാറ്റുമ്പോൾ വിയുടെ പവറിലേക്ക് വരും. സോ ln V raised to gamma is a constant. So we can rewrite this equation as ln P യും ln V raised to gamma ln common ആയി P V raised to gamma. നമുക്കറിയാം ln പ്രോപ്പർട്ടീസ്. ഇത് മൾട്ടിപ്ലിക്കേഷന് നമ്മൾ ln എഴുതുമ്പോൾ ഇങ്ങനെ വരും. ഓക്കെ, so this is ln P V raised to gamma is a constant. From this expression P V raised to gamma is a constant. ഈ എക്സ്പ്രഷനിൽ നിന്നാണ് P V raised to gamma എന്ന് പറയുന്നത് കോൺസ്റ്റന്റ് ആണ് എന്ന അഡിയബാറ്റിക് പ്രോസസ്സിന്റെ ഇക്വേഷൻ ഓഫ് സ്റ്റേറ്റ് നമ്മൾ കണ്ടുപിടിക്കുന്നത്. എങ്ങനെയാണ് ഇക്വേഷൻ ഓഫ് സ്റ്റേറ്റ് ഓഫ് അഡിയബാറ്റിക് പ്രോസസ്? P V raised to gamma. എന്നിട്ട് നമ്മൾ അതിന് ശേഷം മാറ്റി എഴുതിയിട്ടുണ്ടായിരുന്നു. പിക്ക് പകരം വിയും ടിയും പിയും ടിയും ഒക്കെ വെച്ചിട്ട് നമ്മൾ എഴുതിയിട്ടുണ്ടായിരുന്നു. ഓക്കെ, so this is the equation.
Now, today we discussed about first law of thermodynamics. So what is first law of thermodynamics? That is, when we give a dq amount of heat to a system, it is used to increase its internal energy and also used to do work. So it is nothing but another form of law of conservation of energy. In mathematical formulation, we can write the first law of thermodynamics as dq is equal to du plus p dv. Thank you.